Okay, blood supply to the kidneys and through the kidneys. Kidneys, like it states here, 15 to 30% of total resting cardiac output. I'll just put it this way: kidneys require a substantial amount of blood pressure and blood flow. If a person's having an issue with loss of blood, heart problems, and blood is not flowing through the kidneys correctly, the kidneys will shut down. So here is the pathway. I have it here for you all the way to the glomerulus, and then I tried to make it as you're leaving. I didn't really want to make these going this way, but I think you get the idea. So here's the renal artery. You see it coming in. Now, the very first branches off of that is called the segmental artery. And then here's, of course, the renal vein, and you'll see they both go along the same pathway. So blood going in and through the kidney to get filtered, and then leaving the kidney, it's all along the same pathways. Up between, here are the pyramids. These are called the interlobar arteries and veins. And I can get this a little, it's going to kick me out. Get this a little closer, you can see it right there. And then as they come up and they start kind of flattening out on the top, these are called the arcuate arteries and veins. Let me see on our diagram. I see interlobar. That's okay. The other diagram has those, but at the top, here's the artery, here's the vein. And see the smaller branches? Those are called the interlobular arteries and veins. And the artery is what leads into what is called the afferent arteriole that goes into the glomerulus and then leaves. It's called the efferent arteriole here in your PowerPoint. See the afferent arteriole coming in, and see there's the glomerulus and it's leaving. And it's showing the arrows. The blood is being filtered as the blood passes through the glomerulus. And then it's going to leave, like I said, through the same pathway. Okay, so I'm going to back this up a little bit more. So the renal artery, the segmental artery, interlobar artery, arcuate artery, arrow comes to here, interlobular artery, which are the ones out here in the cortex, the smaller ones. Afferent arteriole into the glomerulus. Now, on the other diagram I gave you, so here's the arcuate artery and vein. See that? That would be the arcs of the top. The smaller branches blown up, the interlobular artery, interlobular vein, and see how this comes around that way, and it forms what is called the afferent arteriole. Goes into the glomerulus, and then here it's exiting as the efferent arteriole. Now I went ahead and left these off, and you can see that at some point it's going to join back to this interlobular vein, and then it's going to go that way, and it's going to leave the same way it came back in. So blood goes in this way, it gets filtered, okay, then passes through the efferent arteriole, and then along the way, in this area here where the capillaries are, is where you have all of the what's called reabsorbing going on. So blood comes in, it gets filtered, and all the things that want to, it filters almost everything, but specifically urea, uric acid, and creatinine. Those are the toxic products that the kidneys are trying to get rid of. Urea is from the breakdown of protein, uric acid from the breakdown of nucleic acid. So those things are toxic, and they have to be. That's what the major constituent of urine is, are those three basic things, and water and some bacteria and some mucus and some other things. But interlobular vein, arcuate vein, just like it's showing there. And then it's going to go back, if you start up here, see it go back through the interlobar vein, the segmental vein, and then, which are these. And so, that are coming back. And then anyway, it goes through the renal vein. That's a little low on the interlobar vein thing, but that's fine. And then it's going to leave. And then it will eventually go back to the inferior vena cava. And then it's going to go back to the heart again. So that is blood flow through the kidney, into the glomerulus, leaving the glomerulus, and then going back out and exiting the kidney. So here's a real short little summary of that whole flow. Okay, on blood flow through the kidney, or the vascularization, I should say, here is, you can see here on a little display, it says inferior vena cava. There is the aorta. Now it says the abdominal aorta. And you see towards the bottom. So here's, all of this is down here where the pelvis. There, the iliac. See, this is the common iliac and the abdominal aorta. There's the adrenal glands on the top, up here. Now, let me move our little display out of the way. Let's go ahead and just, well, hold on. Okay. This coming in this way, and it just says renal. This is the renal artery. This is the renal vein. If you get a little closer, the one going through here is called the segmental artery. There's also a vein for that. And then you can see, if I can get this to mind me, the ones going up, this is called the renal columns. See, these are called the interlobar arteries and veins. The ones on the top that make the little arcs appear are called the arcuate arteries and veins. There. And then the ones in the very outside out here are called the interlobular arteries and veins. And then those are the ones that the interlobular artery goes into what's called the afferent arteriole, which then goes into the glomerulus and then leaves as the efferent arteriole. And then the blood flow going in is going to go out basically through the same pathway. And blood leaving the kidney, of course, blood coming in is coming through the renal artery. Blood leaving is going to go through what's called the renal vein and then back to the inferior vena cava there. All right. I hope that helps. Just good to see a little 3D representation. Now, what I have here, this is a chart of the entire nephron. Here's the renal corpuscle, which is the glomerulus, and the renal capsule or glomerular capsule. Here's the proximal tubule, convoluted tubule. Here's the nephron loop, or loop of Henle, Henle. Here's the descending limb. Going up this way is the ascending limb. And then what you have all in here is called the distal tubule. And then that's where the nephron would end. And then this is called a collecting duct. And you can see the locations here. Here's the renal cortex. All of this under here is the renal medulla. So we're going to go through the steps of urine formation, and then the last video will be everything that happens after this. So it's broken down here into sections all the way through the collecting ducts, and then urine becomes concentrated, and then the exit all the way out through the bladder. All right, so that's anyway, that's where we're going to start. So I'm going to go back up here. Okay, blood entering the kidneys. Now I just showed you the afferent arteriole contains impure blood, evil blood, needs to be filtered. The blood then goes through the glomerulus, and before I even, okay, I'm going to go through this with you, and then I'll show you this graph that really emphasizes what we're talking about. Under high hydrostatic pressure, filtration of filtrate, which whatever goes through the glomerulus and is filtered becomes what is called filtrate. The glomerular capsule will capture that. Okay, it's going to get captured here, and then it's going to start going down through these tubes. That's what's filtrate. It's the part that was filtered from blood. Water, glucose, sodium ions, chloride ions, amino acids, and waste such as urea, uric acid, and creatinine. Approximately 170 to 180 liters a day, or roughly 45 gallons. Now you have to remember, that's what's being filtered. Nobody urinates 45 gallons a day, not even camels. I want to show you, this is in your PowerPoints kind of later on, and it's talking about the glomerular filtration rate, which we're not going to do any calculations with that. But this is a great diagram. See this big bar here, and it goes all the way up. This is in liters, and up here is about 180 liters. This is what's filtered through the kidneys daily. This over here represents the amount of urine that a person actually loses per day. So that's a small amount. It says up to 2.5 liters, and this is 180 liters. So obviously 98% of everything that gets filtered is going to end up back in the bloodstream, back into the body. So that's what this represents. This is the amount that's filtered. This is actually the amount that makes it all the way through the nephron, through the kidneys, and then exits the body on a daily basis. Depends on a lot of things, but okay, so that's what you want to keep in mind. Almost everything that gets filtered at the area of the glomerulus is going to be reabsorbed back into the bloodstream. That way the kidneys can select what stays and what actually goes. All right, next, the glomerular capsule catches filtrate from the glomerulus like a funnel. If I go back up to that picture I had earlier, which I believe it's this one, maybe one more. Well, this one will work. I would love to make that a little bigger, but here's the afferent arteriole, here's the efferent. So blood's coming in and it's making the bends, and you can see the green arrows here. They're showing what is being filtered, what will fit through these little openings in the glomerulus. And it's being captured by the glomerular capsule or Bowman's capsule. And then it's going to start going down the proximal convoluted tubule. Each kidney has 1 million of those. So that's how the kidneys are functioning. The proximal convoluted tubule. Now this is important. Reabsorption of about 80% of the useful products in filtrate, water, glucose, amino acids, into the blood and kidney tissue. You have to remember glucose is an abnormal part of urine. It shouldn't be there. It actually gets actively transported out of the renal tubules back into the bloodstream. Shouldn't have glucose in urine unless somebody just ate a bunch of birthday cake or they have diabetes. So to go a little further on, in your PowerPoint here, this is a really good slide, this one. Here's a glomerulus, here's the afferent arteriole, here's the blood leaving after it's been filtered, the efferent arteriole, and then you see it going down this way. So all that filtrate is captured by the glomerular capsule, and you see when it starts going down through here, the proximal convoluted tubule, 80% of it, look, is being pumped out. Water goes by osmosis, but sodium ions, they're pumped out. It's not showing it here, but glucose is being actively transported out. This is nitrogen. It says negatively charged ions are attracted to positive ones. So if sodium is being pumped out, chloride, phosphate, bicarbonate are following it. Water moves out by osmosis because the osmotic pressure here is going to be stronger than the osmotic pressure here. So water is always drawn to higher osmotic pressure. That's what osmosis is. So 80% of everything that was filtered goes right back into the bloodstream, right back into the kidney. Now the descending loop and the ascending loop of the nephron. So the next part of this tube ride, and I have another picture for that, which is up. Well, yeah, this is interesting. Okay, we'll fix that. All right, so here it is. Here's the glomerulus. See, here's that proximal tube. Now, here's the nephron loop. Now, this is kind of a busy diagram, but I liked it because down here it shows when that filtrate is going down through this area, it's called the descending limb, this side is permeable to water. See, it says water is being pumped out because the whole goal of urine formation is to get rid of all the toxic products with minimal loss of water. And it's actually showing it there being, here's water, sodium, glucose, and this is actually showing the area of the proximal convoluted tubule. That actually does have glucose. Now, once it gets to this point, this is the descending limb, water is moved out by osmosis. This side is permeable to water. Okay, then the filtrate makes a turn and starts going up what's called the ascending limb. This side is not permeable to water. And it's showing sodium and chloride ions are being pumped into the kidney tissue. Kidney tissue is very hypertonic. So that way it can control, when water is permeable, it will move out of these tubes. This is the the distal convoluted tubule. It says controlled by hormones, more water reabsorption, sodium chloride, and then you actually have hydrogen ions being added to this area. Remember, urine is very acidic. This is actually showing, I'm sorry, I'll stay with the distal. Anyway, this area is where hydrogen ions get added. Urine is acidic. It's antimicrobial. It'll kill microbes. So to go back up, so the distal loop, more reabsorption of water into the blood. The ascending loop going up, sodium and chloride ions are actively pumped out. Water is impermeable on that side. And then, like I was saying, we get to the distal convoluted tubule and the collecting ducts. Now, along the distal convoluted tubule, so now we've gone through, here's the proximal. This is everything that's going on with that. Here is the descending loop of the nephron loop. It's permeable to water. The side coming up is not permeable to water. That's more ions being pumped out. So now we're talking about this area here, so the distal convoluted tubule. Hydrogen and potassium ions are secreted into the nephron at this point. And it's kind of showing this here. It's a little confusing, but it's going from the blood. See that? It's actually moving into this area. You can see that there's some more hydrogen ions going into the renal tubules. It's the way that the kidneys can control or help control acid-base balance of blood. But these two areas are under control of hormones. And the distal convoluted tubule is the end of the nephron. And that's an area where more water can be reabsorbed. It's just under the control of hormones. ADH specifically, and aldosterone. The collecting ducts, same thing. They are under control of ADH and aldosterone as well. And even more water can be reabsorbed there. So this is a good diagram. So here's the glomerulus. See, there's the proximal. And then, like I said, here's the descending limb. See, water's moving out. Here's the ascending limb. And on the distal tube, it's showing more NaCl here being excreted out of these tubes. But it even says, in the absence of ADH, solutes are reabsorbed while water remains in the filtrate. So what that means, and there's another slide here that shows this really well. It's this guy. This is in your PowerPoint. Antidiuretic hormone, remember, makes the kidneys conserve water. So this says low ADH levels in blood, you have dilute urine. See, the water stays inside the renal tubules and the collecting duct, and then it leaves the body. If a person's dehydrated, or they're in a situation where the body wants to conserve water, high ADH levels, and you see water is now permeable to the distal and the collecting duct, and more water is moving back into the kidney tissue and will end up back in the bloodstream. All right. It says urine becomes concentrated further because more water is reabsorbed in the blood. So at this point, now once you reach here, which is the this is a collecting duct. You see at the bottom down here. Whatever reaches that point, there's no more reabsorbing. It's going to leave the body. So it goes through the renal pyramids, the calyces, I showed you that, into the renal pelvis, ureters, bladder, urethra, which is the exit to the body, and then the outside of the body. So if you remember with our little summary, we started out with 180 liters, and like it says here, approximately 1 to 1.5 liters every 24 hours on average. So 98% of everything that got filtered did not leave the body.
Each kidney includes over 1 million blood filtering units called nephrons. Blood enters the nephron through a capillary bed called a glomerulus. It is surrounded by a cup-like structure, the glomerular capsule, which is the beginning of the duct called the renal tubule. As blood flows through the glomerulus, blood pressure forces it against a specialized layer of cells that surrounds the capillaries. The layer of cells blocks blood cells and proteins, but lets waste and water pass through the glomerulus and into the glomerular capsule. The filtrate then flows into the proximal convoluted tubule. This process is called glomerular filtration. It is the first step in urine formation. Glomerular filtration produces a plasma-like filtrate containing waste, but also water and other substances the body needs. As the filtrate passes out of the glomerular capsule and through the renal tubule, substances like water, essential ions, glucose, amino acids, and proteins are reabsorbed into the body through cells along the tube wall. At the same time, additional waste ions and hydrogen ions still in the blood pass from capillaries into the renal tubule. This process is called secretion. This process of reabsorbing water and nutrients and secreting additional waste creates urine. The urine passes out of the kidney, through the renal pelvis and ureters, and into the bladder.
Okay, let me cover this and we're gonna stop this video. As far as filtration goes, back to our slides. It's not that one. It's this one. If you'll notice here, this is supposed to be a glomerulus, one of the little capillaries you see. Here is glomerular hydrostatic pressure, the pressure inside the glomerulus. Here is the capsular hydrostatic pressure, so the pressure in the capsule surrounding the glomerulus. And here is the osmotic pressure of blood. Now, we're not going to do any math, but it's showing hydrostatic pressure is what's created by heart contractions. This pressure has to win. And even down here it says outward force. Glomerular hydrostatic pressure is about 60. It says the plasma osmotic pressure is 32. The capsular pressure is 18. So we have a net filtration pressure of 10. Yeah, that pressure is what causes the kidneys to filter blood. The glomerular hydrostatic pressure. That one always has to be higher than these other two. It has to overcome these other two pressures in order for the kidney to function correctly. So there's the capsule that has pressure, and the blood itself has what's called osmotic pressure. It's a pulling force, and then the pressure going through here and through the kidneys is created by the heart. So the glomerular hydrostatic pressure, stuff drives me crazy. Okay. Pressure inside the glomerulus created by heart contraction. It is a pushing force that creates the filtration pressure. Always has to overcome the other two pressures listed. Osmotic pressure of blood is a pulling force. It's trying to keep it's trying to keep fluids inside the blood. This has to overcome that. And the capsular hydrostatic pressure is another one that the pressure in the glomerulus has to overcome. There's pressure in the capsule, especially if somebody had a kidney stone, there'd be more pressure. But yeah, this is it. See the glomerular hydrostatic pressure, and this is the filtration rate, but it's just kind of showing that has to overcome these two for the kidneys to function correctly. I'll start there next.